All right, let's talk about polar coordinates. I'll try to keep this brief. If you have never seen polar coordinates before, you need to read the text carefully. This is really just a brief review. So polar coordinates r and theta are related to Cartesian coordinates x and y by the equations x equals to r cosine theta and y equals to r sine theta. We can solve these in some sense for r and theta like so. R squared is x squared plus y squared, and tangent theta is y over x for x not equal to 0. Keep in mind that theta is measured counterclockwise from the positive x-axis, and naturally theta and theta plus 2 pi j for some, this means j element of z, this means j is in the set of integers. Anyway, so theta and theta plus 2 pi j, they describe the same ray from the origin. And to be picky, the origin doesn't have an angle defined, it just has r equals to 0. So polar coordinates, unlike Cartesian coordinates, have some defects. All right, they're not unique. That's kind of a problem. And they're not even defined at the origin. All right. Furthermore, adding more embarrassment still, sometimes we let r be less than 0, sometimes we insist r is positive. If somebody says that r is equal to the square root of x squared plus y squared, and if they really believe it, then r is non-negative, right? But we will soon graph something with r being negative, so you gotta judge by the context. Standard angle is tricky. There's 4 quadrants, and they have different rules. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. Quadrant 1 has angles between 0 and pi over 2, and then pi over 2 to pi, then pi to 3 pi over 2, and 3 pi over 2 to 2 pi. And in these different quadrants, we have sine and cosine, positive and negative, as indicated. I should mention that theta is the inverse tangent of y over x is only a legitimate formula for x positive. In quadrants 1 and 4, this formula works. In quadrants 2 and 3, it will not help you unless you interpret it properly. So here's some examples of that. So if I have the point 2, I can find the standard angle by simply taking the inverse tangent of y over x, which gives me inverse tangent of 1, which is pi over 4. Great, 45 degrees if you like, to the angle to P1. In contrast, minus 1 also has an inverse tangent of y over x of pi over 4, but of course it's not at pi over 4, right? It's over here. You can see from the diagram that we take pi over 4 plus the inverse tangent of y over x. You see we take pi plus pi over 4 to get 5 pi over 4, which is where that actually is. All right. So you gotta think through the standard angle. I mean, there you can look up a formula, but it's got cases. You gotta pay attention to cases. All right. We can talk about how to go back and forth from Cartesians to polars. This is the Cartesian equation, which gives you that polar equation. All right. Of course, some people would also say r equals minus 3 is possible. Fine. Y equals mx plus b is a nice equation in xy coordinates. It's a line, slope-intercept, right? And if you put in x equals to r equals to r, y equals to r sine theta, x equals to r cosine theta, you can solve for r, and this is the line written as a polar graph. As you can see, it's a reciprocal of trig functions. It's quite ugly. So, alright, fine. So, moral of the story, circles are nice in polar coordinates, lines are nice in Cartesian coordinates. You gotta know, what's the right tool for the job. Continuing on here, if we have a parabola with vertex x naught y naught, then here's what it looks like in polar coordinates. Alright, great. Here's another parabola in polar coordinates. And here's yet another parabola in polar coordinates. In each one of these, I'm taking y and x and replacing them with r sine theta and r cosine theta, and that gives me the corresponding polar equations, right? This example is a little bit more in depth. Here I look at ed over 1 plus e cosine theta. This is the polar form of a conic section with eccentricity e. E less than 1 gives us an ellipse, e equals to 1 gives us a parabola, e greater than 1 gives us hyperbola. Properly understood, as e goes to 0, we get a circle. I don't know if you can really see it from here without digging into the details of where this came from, but what I will do is take this and convert to Cartesian coordinates. To do that is probably instructive. And it's pretty straightforward. What I do is I first of all rewrite it as an equation, multiply by the denominator, and then what I do is I put in r as square root of x squared plus y squared. I leave the r as r cosine theta, but that's ed minus, that's an x, right? And then I square both sides, and I collect things together. Assuming e is not equal to 1, I'm able to divide by that and clean things up a little bit. Eventually, I get to this expression down here, x minus that squared plus y squared times that is equal to this quantity. And you can see that if e was greater than 1, that would make this like a plus, a minus, which would give us a hyperbola, as I claimed. On the other hand, if e is less than 1, we're going to have like a positive and a positive equals to something positive over here, which would tell you it's an ellipse. And it's hard to see. You can't really see it from here, but if e equals to 1, something else happens, and apparently that's a parabola. Now, the formula for the ellipse that I think is interesting is probably better down here, because, of course, a lot of times I like to think about the ellipse that's known as a circle. And so in polar coordinates, ellipse with focus at the origin and semi-major axis A and eccentricity E is given by this formula. R is equal to a times 1 minus e squared over 1 plus e cosine theta. So here's a picture of it. You can think about the sun, then you got perihelion and aphelion, and we put this, the sun is at the origin, and theta sweeps around. Like when theta equals to 0, we've got a times 1 minus e over 1 plus e, which gives us a times 1 minus e. And when we have theta equals to pi, we've got a times 1 minus e squared over 1 minus e, which leaves us a times 1 plus e. So we're furthest away from the sun at pi, we're closest to the sun at theta equal to 0. And in fact, the eccentricities of planets are well known to be close to 0 for most of them, which means they're almost circular, but not quite. But anyway, polar coordinates are really nice to study ellipses if you get into it. I believe there's a section in your text you can read more about how that's derived and so forth. Next topic here is polar curve graphing. There's a couple different thoughts in here. One is if you're given r is equal to f of theta, you plot r versus theta, and then you translate this to the xy plane using the geometric meaning of polar coordinates. Or step 3, if it's possible to avoid 1 and 2 by algebra, then do that. So my first example 9 here, is algebraically geared. So I'm given r equals to 2 cosine theta. I multiply both sides by r. Gives me x squared plus y squared equals to 2x. Complete the square. I get it's a circle, radius 1, centered at 1, 0. Graphed. Done. Right? Not bad. In contrast, the next example here requires a kind of different technique. If I tried to find the xy equation for this, I wouldn't recognize it anyway. So there's really no much hope in eliminating r and theta at the level of algebra. So what I do is I take my medicine, I draw my graph of r versus theta, like so, and then I just follow the loops. Like loop 1 goes from r equals 0 back to r equals 0 again, ranging from theta equals 0 to theta equals pi over 2. So, of course, theta equals to 0 is this right here, right? Theta equals to pi over 2 is this right here. And that is involving this point, and this part of that graph translates over here to this loop, like that, right? And then next up, we have part 2. We're going from pi over 2 to pi, right? But r is negative. So pi over 2 to pi would be over here, right? But it's negative, so it sweeps back over here. This is the deal. If we have a negative radius, we reflect through the origin. So here I'll keep with this color coding nonsense. And going from pi to 3 pi over 2, we have positive radius, so it is as advertised. From pi to 3 pi over 2, that's in here. So we get that loop, and then finally the final loop. I need another color. Where's my, orange, that'll do it. So this one down here, r is negative between 3 pi over 2, and 2 pi. So you'd think it'd be down here, but since it's negative, it sweeps back up here. All right, like that. And there you go. R equals 3 sine 2 theta is actually a four-petaled flower. All right. It's interesting, if you study cosine, it looks a little different, and you got to be careful. Even in odd cases, don't have to be quite the same. So I should mention that we do allow r less than 0 in such graphing, with the understanding that r theta is equivalent to minus r comma theta plus pi. All right, so that goes back to the way that sine and cosine flip when you replace theta with theta plus pi, if you want to think about it that way. Now, next up then is calculus in polar coordinates. I'm going to stop this and start again for that.